We all know Srinivasa Ramanujan as one of the many great mathematicians of the world. But do we know that unlike many others, Ramanujan spent the greater part of his childhood in poverty and never had any formal mathematical education? Yes, but in spite of all this, his genius was recognized by British mathematician G.H. Hardy when Ramanujan wrote a letter to him stating some of his discoveries. He was invited to England and spent the latter part of his life at Cambridge, working with G.H. Hardy and other mathematicians. He has contributed significantly to number theory and is known for being an intuitive mathematician, finding elegant solutions to complex problems just by the power of his intuition. Today, I am going to present to you some of the many important contributions of Ramanujan that gave mathematicians key new insights and opened course for new research in mathematics. First off, let's start with a rather interesting little tidbit about Ramanujan. As the story goes, when one day Hardy remarked to Ramanujan that the number of the cab he was travelling in, 1729, was a rather dull one, Ramanujan replied that it was not, as it had the interesting property of being the smallest integer that can be expressed as a sum of the cubes of two positive integers in exactly two ways, 1 cubed plus 12 cubed and 9 cubed plus 10 cubed. Thus, 1729 came to be known as a Hardy-Ramanujan number or a taxicab number represented by Ta of n, where n denotes the number of ways in which the number can be expressed as the sum of two cubes, in this case 2. Some other numbers in the series are 2 and 87,539,319, which respectively are the first and the third term in the series. A total of 6 such numbers have been found, and the 7th number and onwards are still waiting discovery. Now let's go on to the contribution of Ramanujan in finding the value of the constant we all love, pi. Ramanujan gave a series to calculate the value of pi. Here, sigma is the summation notation. This series is highly convergent. The higher the value of k you take as the upper limit, the more accurate the value of pi you will get. If we truncate the series till one term and take k up to 0, we get the value of pi correct to 6 decimal places. And if we truncate it to just 2 terms, the upper limit being k is equal to 1, we get the value of pi correct till 15 decimal places. Due to its extraordinarily rapid convergence, this series is used today as the basis of some of the fastest algorithms used to calculate pi. That was a lot of pi. So now let's get into some of the serious contributions of Ramanujan to mathematics. We'll start with the partition function, represented as p of n, where n is any non-negative integer. P of n gives the total number of distinct ways of representing n as a sum of positive integers. This is easy to calculate for smaller values of n, but a really difficult task for larger values. For example, if we take the number of partitions of 4, that is p of 4, it is equal to 5, as 4 can be represented as a sum of integers in 5 distinct ways: 1 plus 1 plus 1 plus 1, 1 plus 1 plus 2, 1 plus 3, 2 plus 2, and 4. On the other hand, if we take the value of n to be 100, the number of partitions of 100, that is p of 100, grows exponentially to nearly 200 million. In fact, the function grows exponentially as the square root of n, and from the graph you can see how sharply it rises. Ramanujan discovered certain properties of this function and further went on to give an expression for estimating the value of the number of partitions. The properties that Ramanujan discovered are known as Ramanujan's congruences. These relate the divisibility of a number to the divisibility of its number of partitions. The first partition is stated as p of 5k plus 4 is equivalent to 0 mod 5. This is just a fancy way of saying that if a number is 4 more than a multiple of 5, that is, it is 4, 9, 14, 19 and so on, then the number of its partitions is a multiple of 5. The second such congruence that Ramanujan proved is stated as p of 7k plus 5 is equivalent to 0 mod 7. That is, if a number is 5 more than a multiple of 7, then the number of its partitions is a multiple of 7. Later on, in collaboration with Hardy, Ramanujan went on to give an asymptotic expression for the partition function. Asymptotic here means an expression that estimates the value based on a limit. For P of 1000, this gives the value 2.4402 into 10 raised to the power 31, which is only 1.415% larger than the true value. Ramanujan and Hardy later went on to lay down the foundations of the Hardy-Ramanujan-Littlewood circle method, which is a useful technique in analytic theory through their work on the partition function. These were just some of Ramanujan's contributions to various fields in mathematics, from number theory to mathematical analysis. Through his intuition, he was able to present solutions to mathematical problems previously considered unsolvable, and has left his mark on the world of mathematics. In his lifetime, he compiled nearly 1300 results. One of his most intriguing achievements is the discovery of Mach theta functions, a complex concept in mathematics. Ramanujan also worked on continued fractions and radicals, and one of his conjectures resonated into the modern world by being the basis of the proof of Fermat's last theorem. Even after his untimely death, his results continue to interest mathematicians. As a parting gift, Ramanujan left all his results compiled in 4 notebooks, known as Ramanujan's notebooks. These notebooks contain all his lifetime's work and continue to shed light onto his mathematical mind. To commemorate him, 22 December has been declared as National Mathematics Day. He continues to be an inspiration to young mathematicians and inspire new discoveries. Thank you for joining me today on this mathematical journey.